Hello Western. In the previous video we studied what happens when a wave reflects off of a fixed end. In this video I want to study what happens when a wave reflects off of an open end. And this is, for example, what happens in a wind instrument. So take, for example, a flute. We can treat a flute as just being like a long pipe. And we have a sound wave that travels through this. Eventually, when it reaches the end of this pipe, it gets reflected off even though there's no fixed point. This is called an open or a free end. And when a wave gets reflected off of an open or a free end, the wave remains right side up. So to illustrate this, I have again this animated GIF of a pulse that's moving towards the right. And when the wave reaches this end, it's going to get reflected off of this free end, but it'll remain right side up. Now, some of you may have actually seen something like this before. If you've ever seen a whip being cracked, this is exactly what happens. You have a pulse that travels down along the length of the whip, and when it reaches the end, it gets displaced by twice the length of that pulse. And that's why the whip makes its cracking noise, because this displacement is very large. It happens over a very quick time that the end of the whip is actually traveling faster than the speed of sound. Now, because the boundary conditions, because the wave, when it gets reflected, remains right side up, the boundary conditions for a standing wave with free ends is a little bit different. So before, when we had a standing wave, the ends had to be fixed. But with a free end, the wave at the ends has to have a maximum displacement. So now we have antinodes at the ends of both ends of the, for example here, a pipe. However, even though we have antinodes at the ends of this, the formula for the wavelength still remains the same. So for example here I have the first harmonic, which has the longest wavelength, and we can see in here I have 1/2 of a wavelength. So once again, the wavelength is equal to twice the length of this pipe. The second harmonic, again, is the same sort of thing. I can see here that this is exactly one oscillation. So just like we had before with the fixed end standing wave, we again have that the wavelength of the second harmonic is just equal to the length of the string. In general, the nth order harmonic of a string that either has both ends fixed or both ends free is given by this formula here. So the wavelength of the nth harmonic is 2 times the length of the string divided by n. So let's consider just a simple example of this. So the example says that when you play a flute, you create a free end standing wave. The lowest note that can be produced by a piccolo has a frequency of 587 Hertz. Given that the speed of sound is 343 meters per second, what is the length of a piccolo? So again, remember that the speed of a wave is related to the frequency and wavelength by this formula. But once again, I wasn't given the actual wavelength, so what I have to use is that for a standing wave, if we consider the first harmonic of a standing wave, right, we get something that looks like this. So looking at this, we can see that the wavelength is equal to twice the length of the pipe, or the piccolo. Plugging this into the formula we have up here, we see that the speed is equal to 2 times the frequency times the length of the piccolo. Solving for the length, we get that the length is equal to the velocity divided by 2 times the frequency. And plugging our numbers into that, we see that the result is 29.2 centimeters. Oops. So now what I want to study is what happens when you have both a free end on one side and a fixed end on the other. Now, an example of this would be if you blew into an empty bottle. You can cause it to create a standing wave, and that's when it makes that noise. Now, when you have this, you have both boundary conditions present. On one side, you have an antinode, and on the other side, you have a node, like you see here. Here I have an antinode, and on this side, I have a node. By looking at these figures, we can see that the first harmonic has a wavelength that's equal to 4 times the length, because all we have here is just 1/4 of an oscillation, or 1/4 of a wavelength. Now, we should say third harmonic here. The next one is the third harmonic. And by looking at this, we can see that there's a half plus a quarter, so it has 3/4 of a wavelength in this little space here, L. Which means that the wavelength is equal to 4/3 times that length. In general, the wavelength of the nth harmonic for a wave where one end is free and the other end is fixed is given by this formula here. 4 times the length divided by the order of the harmonic. And I have this subscript odd here because the standing waves, when you have one end free and the other end fixed, only exist for odd-ordered harmonics. So that's why this thing had to be a 3. You have a first harmonic, and then it skips over the second, and you have a third harmonic, and the next one's the fifth harmonic. Okay? So let's consider another example. This example says, it basically asks us to find how many nodes and antinodes do you have for a fifth harmonic when both ends are fixed, both ends are free, or we have one end fixed and the other end free. So recall that the node is the point on the wave that doesn't move, and the antinode is the point that has a maximum displacement. So here I have these pictures of the first, second, and third harmonic when we have both ends fixed. And looking at this, we can see for the first harmonic, we have a node here and a node here. So there are 2 nodes. We can also see that we have one antinode in between. For the second harmonic, we have 3 nodes. And we have 2 antinodes. Finally, for the third harmonic, we have 4 nodes. And 3 antinodes. One here, here, and here. So hopefully now we start to see a pattern. The first harmonic has 2 nodes and 1 antinode. Second harmonic has 3 nodes and 2 antinodes. So the nth harmonic is going to have n antinodes, but n plus 1 nodes. So the fifth harmonic should have 6 nodes and 5 antinodes. Now let's consider a wave where both ends are free. So looking at this, again, the first harmonic, my first harmonic, we have 2 antinodes, 1 at each end. And I have 1 node here in the center. So we have 1 node and 2 antinodes. Now for the second harmonic, looking at this, we can see we have 3 antinodes and 2 nodes. So it's exactly the opposite as what we had before. Before we had 1 more node than the harmonic, and we had as many antinodes as the harmonic. Now it's the opposite. We always have 1 more antinode than the harmonic. And the reason is because we have to have it at both ends. So for the fifth harmonic, we will have 5 nodes, and we'll have 6 antinodes. Now finally, what happens when we have one end that's free and the other end that's fixed? So looking at these 2 figures, we can see our first harmonic has 1 antinode and 1 node. The third harmonic, because remember there's no second harmonic, that should say third, has 2 antinodes and 2 nodes. So actually, if I go ahead and draw what the next one's going to look like, it's not too difficult to do. So let's see, we're going to have something that looks like this. Okay, so we have 3 nodes in here, and we'll have 3 antinodes. So that's what we have for the 5th harmonic. 3 nodes and 3 antinodes. And that's where I'll end the video now, and the next video we'll start up talking about something called beat notes, which is this sort of wah wah noise that you hear when you have a guitar that's out of tune, or sometimes you hear it when the engines in a plane are starting up.